Okay, so if you remember last time we started talking about the vectors, this time from analytic point of view, and we learned that every vector for us from now on can be also assumed to be a triple of numbers. So if I say a vector u, we can write it as three numbers, u1, u2, and u3. And then we realize what the interpretation of these numbers are. For example, if I say u is equal to 1, minus 2, and 3, this means that this is a vector that takes me 1 unit in the positive x direction, 2 units in the negative y direction, and 3 units in the positive z direction. So that are the interpretations. That is the interpretation of the components of a vector, which is different from the coordinates of a point. And then we learn how we can do whatever we have learned in using these components. For example, we learned that if I want to find the opposite vector, it is very simple from algebraic point of view. I can simply multiply the components by a negative sign. If I want to multiply a vector by a number, I just take that number and multiply it on every component. If I want to add two vectors, I can just add them component-wise, but I just told you that make sure that you understand this is not something, it is not a new definition. It is exactly the old definition that we are translating it into this new picture of analytic approach. And then we also learned that if I have two vectors, I want to subtract them, I can subtract them component-wise. Yes, but then we wanted to understand the next operation, that was the dot product between vectors. If you remember, I had to introduce you the notion of these unit vectors, I, j, and k, on the x and y and z axis. I told you that they are famous, so you need to know them. And then if I ask you what are the properties of them, if I ask you what is I hat is the unit vector on the x direction. So if I ask you what are the components of this, hopefully you remember that is 1, 0, 0. And then what is the other one? J, that is the unit vector on the y axis. And then the components are 0, 1, and 0. And this similar thing for k, so that is 0, 0, 1. And these are usually the names we use in mathematics. Sometimes we also use x hat. Might be that is a better notation because it tells you the unit vector for the x-axis. And then you can use y hat, that is the unit vector for the y-axis, and z hat for this one. It depends which book you are studying. Might be you have different notations there. And then what is the good point about these three vectors is that every vector that you have, you can write it as a linear combination of these vectors, yes? If I give you a typical vector like this, immediately, if I want, I can write it as the first component multiplied by I hat, the second component multiplied by j hat, and the third component multiplied by k hat. So if you multiply this one by u1, it becomes u1, 0, 0, and the same thing happens here, it becomes 0, u2, 0, and then 0, 0, u3, and if you add three vectors, it becomes exactly that vector. So you can decompose a vector, any vector that you like, and write it as a linear combination of these three vectors. And then the goal was this. If I give you two vectors, let me give you vector u, u1, u2, and u3, and I give you another vector, v1, v2, v3, and if I ask you what is u dot v, yes, we learned how to calculate this, and then I told you that it is better to memorize this formula so that we can use it. So how did I do that? Do you remember? For u, I wrote something like this. For v, I wrote something similar. And then I used the distributivity of the dot product and multiplied them. But whenever I multiply them, so if I want to do that, it becomes u1 I hat plus u2 j hat plus u3 k hat. Yes, and dot product by the same thing for v, v1 I hat plus v2 j hat plus v3 k hat. And then I started multiplying them term by term. There will be 9 terms, but 6 of them will vanish, only 3 of them will survive. Yes, the reason is that if I ask you what is I dot I, I dot I is the norm of the vector. So you know that any vector dot product by itself is equal to the norm of that vector squared. This we had before, yes? So that's also true for this one. So it becomes the norm of that vector squared, but that's a unit vector, so it becomes 1. And it doesn't matter if I multiply, if I dot product j with j, if I dot product k with k, all of them will give me 1. But if I dot product two different vectors in this, then it becomes 0, yes? And the reason is that I and j are orthogonal to each other. And the same thing for I and k, the same thing for k and j. So if I start multiplying things, this multiplied here, this term will survive. It becomes u1 v1 I dot I, but I dot I is 1, so that becomes u1. But if I multiply this by that, I dot j comes in, but I dot j is 0, so that is ignored. So you can continue this one and convince yourself that these are the three terms that will survive. So this I want you to memorize. So if I give you two vectors, and I ask you what is the dot product, of course you already had a formula for that. The dot product of this from geometrical point of view and definition point of view was the norm of the first vector, the norm of the second vector multiplied by the cosine of the angle two vectors. That was the definition. That was the definition of the dot product, but I want you to understand I am using this definition here to conclude this formula. When I wanted to calculate these things, yes. How did I calculate I dot j? In principle, I wrote norm of I, norm of j, cosine of the angle between them. And the cosine of the angle between them was 0, so that is the reason. So this formula is actually the definition of the dot product. I am using it here to get a new formula in this new context, yes? Okay, so that's good. Okay, let us solve some problems to increase your skills here. Okay, so a very, very simple example. We can do them together. And if the problems are a little bit harder, I will wait for you to think a little bit about them. But these are simple problems. Just let me write them. So example. So let U be this vector 1, 2, and 3, and V be the vector -3, 0, and 1. Part A, determine U dot V. Part B, determine two U plus 3V dot minus U plus V. Yes. Okay, so let me make the dot very clear here. Okay. So we want to determine these two. So of course we know that the answer, the output to these calculations in both cases will be a number, yes, because that is the dot product, and the answer to a dot product is to be a number. Of course, these are very simple ones. So if I want to calculate U dot V, what I am supposed to do, I am taking the first component of the first one, 1, and multiplied by the first component of the second one, plus the second component of the first one multiplied by 0, and then I will have plus a 3 times 1, yes? And if you calculate this number, it becomes 0. So what can you conclude about these two vectors? Because the dot product happens to be 0, am I right in my calculations? Yes, -3, 0, and 3, yes. This happens to be 0, so it means that these two vectors are perpendicular, yes? Part 2, for part 2, what I am supposed to do, you can do it two different ways. You can first use distributivity, okay, and then calculate that. Or you can make the components of this vector the components of this vector and then dot product them. So it doesn't matter here. But of course here, because u dot v turns out to be 0, might be it would be easier if I just distribute. Yes, because if I distribute, this becomes the norm of u. But this term will vanish. This term also vanishes. And this term will become the 3 times norm of v squared. But let me just do it normal way. So I would say that I will calculate 2u plus 3v first. So this means that I multiply the components of the first vector, which is 1, 2, and 3 by 2, and then I will write 3 times minus 3, 0, and 1. Then what happens here? This becomes 2, 4, and 6. The other one becomes minus 9, 0, and 3. And then I add them, it becomes minus 7, and 4, and 9. And I do the same similar calculation for this. So this becomes negative of u, 1, 2, and 3, plus v, which is minus 3, 0, and 1. And then it becomes minus 1, minus 2, minus 3. And then I add it to minus 3, 0, and 1. And then what I get is minus 4. Please watch my calculations. And then minus 2. And finally, the question mark is the dot product between this vector and that vector. And I have a triple for the first vector, and I have a triple for the second vector, and I know how to do that, yes? So I have to take the first component, multiplied by the first component, the second component multiplied by the second component, and the third one by the third one, and I add them. So it becomes 28 minus 8 minus 18. So it becomes 2. Yes? Okay, so that is a very, very simple example. Another example that is very common in this text, so in this context, so let me also write this, that's also very simple. Determine M such that the vectors u equals to 2, m plus 1, and 1, and v equals to 3m, 2, and m plus 2 are orthogonal. So I hope I can. So you see, I think this example is also very simple, but this is very common. So I told you that whenever you want to say something about orthogonality, it's probably better to think about the dot product. So we want to determine M so that these two vectors are perpendicular, yes? So we know that U is perpendicular to V if and only if U dot V is equal to 0. But I know what is U dot V. The first component multiplied by the first component. The second component multiplied by the second component. And finally the third component multiplied by the third component here. This is the dot product, and it is supposed to be equal to 0. And then I can solve this equation and find it. So it is 6m plus 2m plus 4, and then I have m plus 2 equals to 0. So this becomes 9m equals to minus 6. Then it means that m is minus 2 over 3. Yes. Am I doing some mistakes because the number I calculated back then is different? You see, Might be I have written it differently. Let me check. 2m plus 1 and 1, 3m, 2 and m plus 2. So 2 times 3m, yes. Yeah, I don't see any problems right now here. Do you see any problems here?
I think it's m plus 1. Yeah, you wrote m plus 2 in your calculation.
Okay, thank you.
But
This one.
yeah.
Yes, thank you. Yes. So then it becomes what? 2m plus 2, and then it becomes 4 minus 4. Yes, now that is the answer that I had done it before. So it is 4 over 9. Thank you. Okay. Another example, I don't know, let me remind you of something about this. These are actually important ones. So do you remember if I have a vector called, let me call it vector v, and then I have a vector u, I can talk about the projection of this vector onto this vector. Yes, this vector that you see here is called the projection of vector u on vector v. Yes? And we got a formula for that, if you remember. It was projection of vector u onto vector v. We learned that it becomes u dot v divided by the norm of v squared v. That's a very important formula in linear algebra. These type of calculations are actually, this is good to know, or at least know how to find it. And then we also learn what is the reflection vector. If I call this reflection vector, for example, u prime, if you go back and see some of the lectures we had before, you should be able to find u prime as well. It's not a hard problem, so you can just, these are very famous ones. I want you to remember the formula, or at least how to find them. So u prime would be u minus that vector, 2 times that vector. Yes? So, yeah, these are important formulas. I want you to know at least how to find them. So, if you go back here, but this one, why is that true? Because you remember, if you want to find u prime here, you can, u prime is equal to this vector plus this vector from here to here, yes? So let me call this vector w. So then u prime is the old vector that you have plus w, yes? But if I ask you what is w, a w is 2 times this vector from here to here. But what is this vector itself? This vector from here to here is the projection vector minus vector u. So this is projection of u on v minus u. So if I ask you what is this vector from here to here, this vector is this one minus that one. This one is called the projection minus that one. But I already know the formula for the projection. So what I have to do, I have to multiply it by 2 to get w. So w becomes u plus 2 times this vector. If I multiply 2 there, it becomes, so I made a mistake there. That is not correct. That's the reason that I'm just calculating, because I had forgotten the formula exactly. So this becomes minus 2u. So then you see what happens. 2 projection comes first. U minus 2u becomes minus u. So I have to reverse the order, yes? So that is u prime. So you see, let me just repeat. This is one of our old lessons, so if you don't follow exactly, I did it quickly, you can go and watch the video. But these are important skills that I want you to have if you want to work with vectors. So one thing that you need to be able to calculate is how to find the projection of a vector onto another vector. So you should be able to convince yourself again that is the formula. If you have forgotten, you can watch the video for the proof. But then another thing that you need to learn is how to find the reflection of a vector about a vector. So this means that I want to reflect this vector along this vector, I get u prime. I want to be able to write u prime in terms of my vectors u and v. Hopefully you realize that u prime, this vector, is nothing except u plus this vector that I call it w. But if I ask you what is w, w from here to here is 2 times this vector from here to here. And now if I ask you what is this vector, it is this vector u minus this vector projection. Yes? Sorry. The projection vector minus that. And then for w, I have to multiply this by 2. When I multiply this w by 2, this will 2 will be multiplied here and there. And then this u minus 2u is negative u, which is this one. And 2 times the projection is this one that I have written. So these things are important to be able to get it if you forget. Okay? So let me give one example in this regard. Example. Consider the vectors u equals to 1, 1, 0, v equals to 1, 2, 1, and w equals to minus 1, 1, and 1. Consider the following vectors. Determine the reflection of vector u with respect to the vector say v minus 2w. So you see that now you have you can use algebra to calculate a lot of things, yes? If you want to do it from geometrical point of view, it is not that easy. You need to draw the vectors and then find this vector and try to reflect that vector in space through that one. But now you can do it very easily, analytically, yes? So how can I do that? I am supposed to reflect this vector with respect to this vector. So the first thing that I have probably to do is to find the components of that vector. So the components of that vector are easy to calculate. So v minus 2w is equal to v is 1, 2, and 1 minus 2 times w minus 1, 1, and 1. So let us do it in our head. So 1 plus 2 is 3, 2 minus 2 is 0, and then 1 minus 2 is minus 1. Yeah, and please check my calculation. Yeah? Am I right? So that would be to this vector. This vector here is playing the role of this vector that I'm reflecting over it, yes? This vector u is the same vector in the problem. I want to reflect u with respect to this one. So in this formula, wherever you see v, you have to replace it with v minus 2w. So if I want to answer that question, I would say that u prime, the reflected vector, is equal to something like this. U is the same in this formula, but v has to be replaced by this combination. Yes, so this becomes 2, and then I have u dot v. So now it becomes u dot v minus 2w, and then divided by the norm of this vector squared. Yes, and then multiplied by the same vector. And then after that, minus the vector u. So you have to calculate this. And that is easy, even though it seems horrible, but this is very easy because u is a triple. This one at the end is a triple. So I know how to dot product two triples, yes? So I just follow the calculations. So I put a 2 there. Okay, we can do it in, we can write it. U dot this one. So U is that one, this is 1. I multiply 1 by 3. I multiply 1 by 0. I multiply 0 by minus 1. Yes? In the denominator, I have the norm of my vector squared. But in the previous session, we learned if you give me the triple of a vector, and if I want to find the norm of a vector squared, what I'm supposed to do, raise these numbers to power 2 and add them. Yes? So it becomes 3 to power 2, 0 to power 2, plus minus 1 to power 2. Any questions so far? Yes?
Don't you take the root?
No, the root takes if I don't have this power 2.
Ah, okay.
This is norm squared, so I don't have the root, yes? And then I find this number and I multiply it by that components. So what are they? 3, 0, and minus 1. Then I subtract that u at the end, which is 1, 1, and 0. Then this is a simple calculation, yes? So this is 9, this is 1, this is 10. So it is 3 over 10. But when I multiply it by 2, it becomes 3 over 5. Then it becomes 3 over 5. And then I multiply it by 3, 0, and minus 1. And then I have minus 1, 1, and 0. Okay, we can also do this in our head. Yes, 3 over 5 times 3 is 9 over 5 minus 1 is 4 over 5, yes? And then I multiply that is 0, and then that is minus 1. And then I multiply that one, it's minus 3 over 5. Okay, so this is the reflected vector. So you see now the nature of this becomes more calculational, so you're computing things. Okay, now let me give you one question here. I'll solve it myself, then I will give you one question that you can start working on it. It's simple, but I want you to do it. So, example. Let u be this vector 1, 0, minus 1, and v be vector 1, 1, and 0. Determine the angle between vectors u minus 2v and 2u plus 1. Okay, we want to find the exact angle between these two vectors. So what I'm supposed to do, so let me write with blue, so in general it's good to know. So you know that if I am dealing with the angle between two vectors, so one good thing is to think about the dot product. So let me change my letters to A and B. So if I have A with components A1, A2, and A3, and if I give you B with components B1, B2, and B3, and theta is the angle between A and B, how can I find theta in general? What is the recipe? I give you these three numbers for the components of vector A and vector B, and I ask you, okay, to find the angle between them. So how can I do that? Yeah, momentarily forget about the problem, because that is the same problem. Yes?
You dot product them, and then you use the definition.
Yeah, exactly. Because I am calculating one, so I calculate the same quantity in two different ways, yes? I would say that A dot B, I already know the definition tells me this is the norm of vector A, this is the norm of vector B multiplied by the cosine of angle between them. If you give me these, and if you give me these, I can calculate this one and that one. And if you give me these, I can also calculate this one according to the analytic form. And then there's only one unknown left, and that is cosine. So I'm using the not both definitions, the definitions and this theorem for analytic dot product, and I can calculate. So if I ask you what is cosine theta, you would say cosine theta is equal. If you want, you can write a formula for that. You really don't need to memorize that. What is A dot B in general? It's A1 B1 plus A2 B2 plus A3 B3. Yes? And then divided by the norm of A. The norm of A is the square root of A1 squared plus A2 squared plus A3 squared. Yes? And then the dot product of the norm of the other one is this one. So this is a little bit complicated, but it is very easy to use. Yes? So that is the formula for the cosine of the angle between two vectors. You don't need to memorize that. It is better to learn it in this way. So in principle, that is the idea. In this case, I have to find these two vectors. So let us do it in our head. What is u minus 2v here? I have to take u minus 2v. 1 minus 2 becomes minus 1. 0 minus 2 becomes minus 2. And then minus 1 minus 0 becomes minus. You can also check my calculations. Please do that. And then I have 2u plus v. I have to multiply this by 2 and add it there, so it becomes 3, and then it becomes 1, then it becomes minus 2. Yes? Do you confirm?
Yes.
Good. And then I calculate cosine of theta. So let us just do that. Now what I have to do, according to what I told you here, you just dot product these two vectors in the numerator, and then you calculate the norm of them individually and put them in the denominator. So this multiplied by that is minus 3, this multiplied by that is minus 2, this multiplied by that is positive 2, and then I have a square root of these numbers squared, 1 plus 4 plus 1, multiplied by these numbers squared, 9 plus 1 plus 4. And then the numerator becomes minus 3, and then this is the square root of 6, square root of 14. Yes? I would prefer to simplify it if possible. So you need that 1 square root of 2, 1 square root of 2 gives me 2. But then there are 3 and 7 left, it becomes 21. And then I calculate theta. Theta is cosine inverse. I want you to keep the exact value unless you want to do some approximations. That's the exact value of this angle between. This is 6. Yes? Okay, now let me give you one question. I want to do it patiently and then calculate that. Okay, about the angle between, but a little bit different. Example. Okay, I want you to give me the final answer because I have the final answer here, and then I can check that if you've done it right or wrong. So determine M so that the angle between the vectors u2 minus 1 1 and v 1 1 and m be 60 degrees. Is 60 degrees. Okay, so I want to wait for you, okay? It's a very simple one, but I want you to start doing calculations yourself. Let me double check that I have done everything because I want you. 2 minus 1, 1, 1, 1 and m, the angle is supposed to be 60. Yes, that's right. Okay, do you have the number? Not yet, so I can wait a little bit more. Let me just solve that one, okay? Yeah, m equals to 2. So let us see how. Because we know that the cosine, the angle is supposed to be 60. So what is cosine? Do you remember? So this is cosine 60 degrees is equal to the dot product of these two vectors in the numerator, which becomes 2 minus 1 plus m, and then divided by the square root of these numbers squared added. So it becomes 4 plus 1 plus 1. And then the square root of these numbers squared added. So it becomes 1 plus m squared. Yes? This is the equation that you are supposed to solve. Yes? Okay. And then cosine of 60 is 1/2. This becomes just m plus 1. This is just the number, the square root of 6. And then you have a square root of m squared plus 2. This is a root equation, but not a hard one. You need to get rid of a square root sign. So what you do, first of all, I do it like this. This multiplied by that is equal to this multiplied by that. Then I raise both sides to power 2. This becomes 6 multiplied by that. 6 multiplied by that. When I raise them to power 2, this raises to power 2, this raises to power 2, then I have to multiply. But on the right hand side, when I raise it to power 2, what I have to do, I have to use the squaring pattern, so it becomes 4m squared, 2 times the first one times the second one, and the second one is squared. Then I move everything to the left, it becomes 2m squared minus 8m plus 8. I prefer to divide everything by 2 to make it simpler, and then suddenly it becomes very simple. Because this is also, you don't need to solve it because this is factorizable. And then this gives you m equals to 2. Yes. But of course, before that, because that's a root equation, you have to be careful. It might be a false root. If this is a false root, then you would say that it is not possible by fine-tuning m, make the angle 60. But I think this is the right answer. Yes, if you go back and put m2 here, you will get that this is acceptable. So this means that this answer is correct. M should be 2. Thank you. Okay, now let me ask you a geometry problem, Euclidean geometry problem. And this is the problem that I want to ask. The setup is very simple. Here I have a square. Yes. It is hard to draw it precisely here, but you don't need that precision here. So what I know that AB is 4 times AM. So I have this M here, and I know that AB is 4 times AM. This I know. So it means that I divide it by 4, then I will take this point. And then I also know that BC is 7 times CN. What is, where is it? It is here. So I make it smaller. Yes, assume that this is correct. So Cn multiplied by 7, it becomes BC. And then what I ask you, I take this point and connect it here. And I take this point and connect it there. Yes, and then I ask you to find this angle. Yes? So this shows you, this problem is not related to vectors at all. I haven't tested it if I can solve it purely geometrical myself. But I just want to tell you that solving this problem might be hard if you want to do it using geometry. I don't know, do you have any idea how to do it geometrically? Geometrically means, I don't know, Pythagoras theorem, similarities, things like that. But if I want to calculate something like this, it is extremely straightforward, at least, to understand how to do it with vectors, if you have experience. And I'm trying to teach you that skill. So, do you have any idea how can I use vectors to calculate this angle? Yes?
Can you say that the vector dn is, say that dc is 1,
Yes?
then dn becomes 1 in the x-axis and 1 over 7 in the
Exactly, that's the idea. Okay, but you chose 1, but let us not choose 1, because we don't know if that is 1. Of course, you will see it doesn't matter. So what he's saying is that you can consider the length of this square to be num a, for example. Yes? And then if that is the case, you can imagine you have a coordinate system here. You can imagine, you don't need to draw them, okay? And then you can consider this as a vector and this one as a vector. Do you agree that if I calculate the angle between these two vectors, that's exactly the angle wanted in the problem, yes? So I need to find that. But now I can write the components of this vector. If I ask you what is vector dn, you can immediately tell me how many components I have. I have only 2 components because I am on the plane. And then how much this vector takes me to the right? A units, yes? This is the length of my square. And how much this vector takes me up? A over 7, yes? So these are the components of my vector dn. And then immediately I can find the components of the vector am as well, yes? So what are the components? It takes me how much to the right? A over 4, yes? And how much up? A. That's it. And then I calculate the angle between them, yes?
dm or a.
Yes, thank you. dm. Thank you. From here to here. Okay, and then I want to calculate the angle. So the cosine theta becomes equal the 2-dimensional version. So this multiplied by that is a squared over 4. This multiplied by that is what? A squared over 7. Yes? And then what I do, the denominator is these numbers squared, a squared plus a squared over 49. And then this one becomes a squared over 16 plus a squared. Yes? Of course, what Jonathan said is probably better, because I hope that you agree by rescaling this, bigger or smaller, I am not changing the angle. So it is clear the size of the square shouldn't be a problem. So of course, but if you are a little bit skeptical, you can write it a and see that a will be eliminated. And this is easy, yes? So if I calculate the numerator, the common denominator 11, so 7 plus 4, 11 over 28, a squared. And then here, if I take the common denominator, it becomes square root of 50 a squared divided by 49. And then this one becomes square root of 17a squared over 16. And then what happens? This becomes 11 over 28 a squared. The denominator a squared becomes absolute value, but we don't need absolute value, this is length. So 1a comes out from this, 1a comes out from there, it becomes a squared. And you see that this a squared will be cancelled out no matter what the value is. And then I will have this one multiplied by that one. So what is that one? If I want to simplify, the denominator is 7. The denominator of this one is 4. The numerator of that one, I can write it 5 square root of 2. Yes, 5 square root of 2 is another name for square root of 50. But the square root of 17, I have to live with that, yes. And this one and that one are cancelled. 4 times 7 is 28, so that one and that one is also cancelled. So what I get is 11 over 5 times the square root of 34. And it was not possible to get such a number for cosine, and it means that this angle is measured, is calculated exactly to be cosine inverse of that number. And if you want to get an estimate about that, you can punch it into the calculator and get the number. So you see that the starting problem was a Euclidean geometry problem, but we use this vector trick to be able to calculate the angle easier. So this is also good to have in the back of your head. Sometimes you can solve the problem with vectorial arguments easier. Okay. Let me see what time. Yes, we have a little bit of time, but we will not be able to finish this lesson now because there is one important thing coming in. I want to spend tomorrow for it. And then after that, we go to cross-product analytic. Okay, so if I give you a vector, so let me just have this three-dimensional coordinate system here. So here we have x, y, and z, and here is the origin. And let me have this vector, for example. Let me call it vector v with components v1, v2, and v3. Yes? The angles that this vector makes with the three axes are called direction angles. Yes? Because if I give you those angles, the direction of your vector is clear. Yes? But, so these are the standard ones. So this one is called gamma. This angle is gamma. It is hard to draw the picture. So you see, these are in a space, yes? If this is x-axis is actually coming out from the board, yes? And for example, this is the v vector. Let me make it the other color. So this vector x, this is your vector x, and then I have somewhere here this orange vector, yes? This angle is angle alpha. The angle that my vector makes with the x direction is angle alpha, but here I don't know how to draw it. This angle, it's not that big, you see, but anyway, that's alpha, and the angle that this makes with the y-axis is called beta. These three angles are called direction angles. Direction angles. And the cosine of these angles are called direction cosines. Okay, direction angles, alpha, beta, and gamma. Direction cosines, cosine alpha, cosine beta, cosine gamma. So these are called direction angles of the vector. These are called direction cosines of the vector. Yes? There is a very nice property relation between these three numbers. Yes? We want to discover that relation. It's extremely important to note this. I'm exaggerating probably. Extremely important, I don't know what it means, but it is important. Okay. Not the most important thing in life probably, but anyway. So, how do you think I can find a connection between cosine alpha, cosine beta, and cosine gamma? In principle, you should do it now. You should be able to do it. Let us concentrate on cosine gamma. It is better in the picture. How do you do it if you want to calculate cosine of gamma? What do I mean by that? It means that if I give you numbers v1, v2, and v3, and I ask you to give me the number of cosine gamma, use that formula to give me the cosine of gamma. No geometry is involved. No geometry is involved actually. You can solve it geometrically, but you really don't need to do it geometrically. Yes?
You can use the formula.
Okay, the formula with what?
With v and the unit vector.
Exactly.
Yeah.
Because one of the any angle, it doesn't matter, yes? I want to find the angle between gamma, angle between this orange vector and this z-axis. But one of the famous vectors on the z-axis is its own unit vector, which we call it k vector. So my goal is to calculate cosine gamma. But do you agree that if I measure the angle between these two vectors, that is the same cosine gamma? That's it, exactly. So what can I write? I can write, what are the components here? 0, 0, and 1. So when I multiply the dot product in the numerator, 0, 0, and V3 gets involved, divided by these numbers squared added, multiplied by these numbers squared added. Yes? And then what happens? So the numerator becomes just simply V sub 3. This is just 1, and I have to keep it. Yes? That's correct. So if I give you these three numbers, you put these three numbers here, you get the cosine of gamma. But can you guess what will happen for cosine alpha? Can you guess what happens for cosine beta? Cosine alpha, with the same reason, I need to take this into account, yes? I hat. And the I hat is 1, 0, 0. This will change, the order will change, but the number is not changed. This is the same exactly, but in the numerator, instead of having V3 survive, then the V1 will survive, yes? So this becomes V1 divided by this. Yes? Okay, and then the same thing happens here. Okay? So you have the formulas in front of you. But can you discover a relation between the angles, cosine of angles? What can I do? I want to find a relation between cosine alpha, cosine beta, and cosine gamma independent of V1, V2, and V3. Can you discover the pattern? Okay, let me ask you. Can you calculate this in your head? I square cosine alpha, I square cosine beta, and I square cosine gamma, and add them. What will happen? You should be able to say that. Couldn't you calculate it in your head? It's 1. Because the denominators, when I square them, all the denominators become the same number, so I don't need to worry about taking common denominator. That is indeed the common denominator. Agree? And then from the first one becomes, when I square it, the first one becomes V squared, the second one becomes V1 squared, V2 squared, V3 squared. But that's exactly the same thing, so that becomes 1. That's a nice relation. So the sum of the squares of direction cosines is always 1. So if you have a vector and you measure the angle between that vector with the coordinate axes, square them and add them, it becomes always 1, independent of the where the vector is. Yes. So if you, for example, move this one, somehow you are increasing gamma, but simultaneously you are decreasing the other ones, so that the sum of the squares always remain constant value 1. Yes? Is that understandable? Okay. And now let me ask you one question. If I have that vector, I can take these numbers, cosine alpha, cosine beta, and cosine gamma, and put them in a triple. Cosine alpha, cosine beta, cosine gamma. This becomes a vector, so let me call this vector, I don't know. Let me call this vector, let me call it E for the time being. Yes? Now I ask you one question. Do you agree that this vector that I defined in this way, So you see, I start with the orange vector. I start measuring the angles that that vector makes with the x and y and z axes. And then I calculate cosine alpha, it becomes a number, I put it here. I calculate beta, cosine beta, I put it here, and cosine gamma here, it becomes a triple. And that triple represents a vector, yes? It can represent a point, but you can also represent a vector using them. Now my question is that, what is the length of this vector? What is the length of vector E? 2 seconds, 1 to finish. What's the length of vector? Yes?
Square root of 1.
Square root of 1, which is 1. Because if I want to find that, it becomes square root of cosine squared alpha, cosine squared. So this vector is a unit vector. Yes, not a vector. It's a unit vector. Okay, can you tell me what is the direction of this unit vector? What is the direction of this vector? Do you think it lies on the same orange vector or not? Yes?
Instinctively, it feels like it should be the unit vector of V.
Yes, and it is. How we can convince yourself about that? Because let me call, I don't know, let me call let me call the direction cosine, the direction angles of this vector, how can I say? Let me write the direction angles with A, B, and C. Which letters I can use? Okay, let us use A, B, and C. Okay, these are, so assume that this is a vector. Okay, when I draw this vector E, assume that this angle is C units, this angle is A units, and this angle is B units. Now I ask you, what is the cosine, what is the direction cosine of this angle? So the direction, if I ask you to find the cosine of C, what you do? You take the third component and then divide it by the length of the vector, which is 1. So it means cosine of C is cosine of gamma. So it means C is gamma. Yes? So, yes, you are right. So if I want you to understand that if I make that vector is the unit vector here, and that is nothing except of E of V. So this is the V vector. So just you can write it as a remark. So if I give you a vector, and if you want to find the unit vector on that vector, one way, of course, is to take that vector and divide it by the norm of that vector. But you can also write the cosine, the direction cosines as the components. Automatically, you generate EV. So this is exactly V over V. By the way, you can see it in a different way. Let me, if that is hard for you to understand, let me make it more clear. Okay, so before doing that, let me ask you to calculate EV before doing that, yes? You have this vector here, you still don't know this is the unit vector for V, but now I am asking you to do this. How do you do that? Using this formula. 1 over norm of V times V. But what is V? V is V1, V2, V3. And if I multiply it in, it becomes V1 over norm of V, V2 over norm of V, and V3 over norm of V. So many airplanes are going. Are they for military?
Yeah, it's like Christmas. They're flying in a Christmas tree.
Ah, okay. Yeah, if you want, you can take a look. Yes, so here, what I did, I calculated EV according to the old formula. So this becomes exactly this. But if I ask you what is this, this is exactly square root of V1 squared plus V2 squared plus V3 squared. So this component that you see here is exactly what is happening here. And that is cosine alpha. So if I calculate EV from the old formula, I get this expression, but this expression is exactly cosine alpha, cosine beta, cosine gamma, and that is what I have written here. It's good to have it in the back of your head, but the notion of direction angles and direction cosines are important. And this is also important to know, because usually by Pythagoras' theorem, we are used to having the sum of two complete squares to be equal to 1 or something. Do you remember in trigonometry, we had sine squared plus cosine squared of the same angle to be 1, but here we have the sum of 3 complete squares. All of them are cosines. None of them is a sine. That's also good to remember. I think that is a good place to stop. I will let me just write an example for an exercise and then stop, because that will be the last thing that I want to talk before starting the new one. So let me just write an exercise for you. It's a very, very simple one, but I want you to do that exercise. Is there any vector making an angle (45 degrees) with the x-axis and 30 degrees with the y-axis? Motivate your answer. So is it possible to draw any vector that you want in any way, so that when you measure the angle between the vector and the x-axis, it becomes 45 degrees simultaneously, the angle of that vector with the y-axis becomes 30 degrees? Okay, you can imagine it geometrically. You can also do it the calculations. So the next time, tomorrow, I will start with this exercise and we'll continue. Okay? The next lesson is actually quite interesting. Okay, any questions? Thank you.